Okay, so we'll go over the problems that you guys had in the handout from today, Friday, that concern velocity and other rates of change. The first problem, number one, you had a dynamite blast propelling a heavy rock straight up with a launch velocity of 160 feet per second. And we were given the equation for that, and we said that the height, h, is equal to negative 16, I'm going to use x squared plus 160x, where x represents the number of seconds. That means that when we take the derivative dh dx, we have negative 32x plus 160. So here we have the graph. We can see that the highest that the rock goes is, we can figure that out by finding the point right here, which we have a x coordinate of 5 and a y coordinate of 400, which means it took 5 seconds to reach the height of 400. We can calculate that by setting the dh dx to 0, which gives us negative 32x plus 160 equals 0. X is equal to 5. We plug 5 into the equation. We get that the height at t equals 5, or x equals 5, is 400. So this is recognizing that the slope at this point here will be equal to 0, which is why we set our first derivative to 0. So then the next question asked us to find out what the velocity and speed of the rock is when it is 256 feet above the ground on the way up and on the way down. Well, graphically we can represent that by taking our function and intersecting it with the line y equals 256, which gives us these 2 points of intersection A and B. A represents the ball attaining a height of 256 feet at 2 seconds, B at 256 feet at 8 seconds on the way down. Well, now what we're going to do is we're going to set our function equal to, in order to solve this algebraically, we set our function equal to 256, and we solve and we get our values. X is equal to 8, x is equal to 2. And then what we do is we take those values, 2 and 8, and we plug them into our derivative equation, which gives us the velocity. And again, negative 32x plus 160. And when we plug in 2, we end up with a speed of 96. And we plug in 8, we end up with a speed of negative 96, which makes sense that the slopes would be the same magnitude but in the opposite direction. Because at point A, the ball was still headed up, which gave it a positive velocity, and B, the ball was headed down, or the rock was headed down, which gave it a negative velocity. Here we have our derivative function plotted. That's this red line right here. At A prime, at 2, we have a height of 96, or its velocity of 96, and at B prime, we have a velocity of negative 96. Okay, our next problem, we asked what is the acceleration of the rock at any time. To get this, we take our second derivative, which means that we took the derivative of our first derivative, which we said again was negative 32x plus 160, which means that our acceleration is equal to negative 32, which means that our acceleration is constant. The velocity is changing at a constant rate over the entire trajectory of this. Okay, and then finally it asks, when does the rock hit the ground? Well, that we just need to set our original trajectory equation equal to 0 and solve. When we do that, we get two values, x equals 0, x equals 10, and the ball was on the ground initially, which is why we get x equals 0, and then it's on the ground again at this point D when x is equal to 10. And so that's the answer to our question of when does the rock hit the ground. Okay, for our second problem, we had that a particle moves along a line so that its position at time t is greater than or equal to 0 is given by the function s of t is equal to t squared minus 4t plus 3. And again, I will use x instead of t, limitation of GeoGebra. Okay, and so this here, A, is going to set our seconds. And if you watch the point here in the top panel, you'll see that as A proceeds, it's going to move back and forth. And basically the idea is its position along the x-axis is determined by this function. And you can see that it's headed in two different directions. At this point it's heading in the positive direction. We can also see the function plotted in the lower panel, and what that point B gives us is the x-coordinate is the time, and the y-coordinate is the position of A along that horizontal line. And then finally we've plotted the derivative function, which is 2x minus 4. Okay, so the first question says find the displacement of the particle during the first 2 seconds. So that means we need to figure out where the particle was at s is equal to 2, subtract its position at s is equal to 0, and that gives us at s is equal to 0, we were at a position of 3, and when s is equal to 2, we were at a position of negative 1. So the movement from negative 1 gives us a total displacement of negative 4. So we moved from an initial value of 3 to a value at t equals 2 of negative 1, so the total displacement was negative 4. Okay, the average velocity of the particle over the first 4 seconds means that we need to figure out where it was, how far it traveled over the first 4 seconds. So we subtract s of 4 minus s of 0. In other words, we plug 4 into our s of x equation, and we subtract s of 0. And then we divide by 4, which is the number of seconds that over which this travel elapsed. And what we see is that when a was equal to 0, we were at a position of 3. And when a was equal to 4, we were again at a position of 3, which meant that the actual change of location was 0, which meant that our average velocity over that interval was 0. That does not mean it was traveling at a velocity of 0 the entire time. All it means is that the average velocity over that interval was equal to 0. And in fact, when we take a look at the instantaneous velocity when x is equal to 4, that's when we need to use our first derivative, which is ds of dx is equal to 2x minus 4. We plug our value of 4 in for x. We get 2 times 4 minus 4, or 4. In other words, the velocity at time t is equal to 4 or x is equal to 4 is equal to 4. That was the velocity at that point. At what values does the particle change directions? Well, changing directions means that the velocity moves from a positive to a negative. And so we can see that if we follow the trajectory, we can see that right now it's moving to the left. And then at this point, it starts moving to the right. So it changed directions here at t is equal to 2. We can tell that from our derivative graph by looking where the velocity achieves a value of 0. And that's where it's crossing from a negative velocity down here to a positive velocity up here. On this other function, we can see that we've reached a local minimum because, again, our position at this point is equal to, we were moving in a negative direction, and then we switched to moving in a positive direction. So here the function's decreasing, and then from here on it's increasing, and that shows up in the first derivative as positive for increasing and negative for decreasing. Okay. Okay, problem 3 is the storage tank problem. And the function we were given was that the height of the water in the tank, y, is a function of the length of time that the fluid has been draining. And again, we'll replace t with x. And we were given that the function was equal to 6 times 1 minus x over 12, that entire quantity squared. And when we expanded, we ended up with y is equal to 1/24 times x squared minus x plus 6. We found the derivative of that, dy dx, is equal to 1/12 x minus 1. Okay, this red graph here is the function, and that shows the height of the water over the 12-second period of time. And what we can see is that it was draining the fastest at the beginning, and then we can see the slope flattened as we moved closer to 12-second mark. At 12-second, the height of the water reached 0, which means that the tank had been emptied at that point. And so if we look at the derivative graph here, which is, again, 1/12 x minus 1, we see that the rate of decrease of the height is steady, and it means that it's a constantly changing rate of change, but that rate of change is itself constant, which means, in other words, we have a constant acceleration or deceleration in this case. So the rate of a change at which the rate at which the water level is changing, again, is our dy dx, or 1/12 x minus 1. When the fluid level is falling the fastest is at the beginning here, when the rate of decline is equal to -1, which is the value of dy dx at x is equal to 0. And it's slowest when x is equal to 12, which would give us dy dx value of 0, and the water is no longer running out of the tank because there's no water left. Okay, so here again we can see that the water is the height of the water is constantly decreasing. The rate at which it's decreasing slows, and that shows up here by this derivative function having its lowest value here, but the highest magnitude at 0, and then that magnitude moving closer and closer to 0 as the time moves closer and closer to 12. Okay, moving on to problem 4. We again have a particle moving along a line so that its position at any time t greater than or equal to 0 is given by the function s of t is equal to -t cubed plus 7t squared minus 14t plus 8. Again, we'll replace t with x. And so we can see that if we look at the particle up here, it starts at a position of 8, which makes sense because when t is equal to 0, the function has a value of 8. And as we move t, or we change the value of t, we can see that in this case the particle is moving first in a negative direction, now in a positive direction, negative direction, and then continues moving in a negative direction. Okay, so again, we've graphed the function y equals -x cubed, etc., so that we can see that as point B moves, its x-coordinate is the time t, and its y-coordinate is actually the position along the x-axis of our point A. Okay, and we can see that when this particular function is decreasing, our point is moving to the left. When it's increasing, point is moving to the right, decreasing, moving to the left. So it changes directions at these local minimum and local maximum points. Our acceleration function is the second derivative, and so the first derivative is -3x squared plus 14x minus 14, which makes our second derivative -6x plus 14. And so part C asks, when is the particle at rest? Well, that would occur when our velocity is equal to 0. And so in order to calculate that, we can figure out when our particle is at rest by using the quadratic equation and solving our quadratic, because our first derivative is a quadratic. And we can see that it's at rest at the times of t is equal to 1.45 and t is equal to 3.22. And those are represented here by a couple of points, C here and D here. And those have x values of, let me get this b out of the way, those have x values of 1.45 and 3.22. So that's when we can see that our particle is at rest, and that's when it achieves a local minimum or a local maximum, and that's also when our first derivative, or our velocity curve, has values of 0. So the x-intercepts of our velocity curve represent the times when the velocity is equal to 0, so in other words, the particle would be at rest. Okay, then we ask at what values of t does the particle change directions? Those also correspond to points C and D, because it's changing direction when its motion moves, when its velocity moves from positive to negative, or negative to positive, and again, that happens at point C and at point D. So we can see that when our value of t is, we can set it so that it is about close to our 1.4, and we can see right around here, if we start at, let's say, at t is equal to 1, we go up, and right at about 1.4, it switches and starts moving in the positive direction. We'll keep doing this, and we're expecting that at 3.22 it will shift again, and so we can see that when it gets to t equals 3.2, then it starts to move in the opposite direction and starts to go negative direction again and stays going in that direction. So again, the minimum and maximum points for our function, original function, and then the x-intercepts for our first derivative show us when the particle changes direction. Okay. Okay, problem 5. And we have a graph that shows us the velocity of a particle moving on a coordinate line. And we're first asked when the particle moves forward, move backwards, speed up, slow down. So since we're looking at the velocity here, it's going to be moving forward whenever the velocity is positive. So that would be over the interval from 0 to 1 and from 5 to 7. It's moving in a negative or backward direction when the velocity is negative, which would be between the time t is equal to 1 right here, down up until t is equal to 5 right here. The particle's acceleration is going to be positive when the speed is increasing. And that's happening over the interval from 3 to 6. We can see that the acceleration is positive when our velocity is increasing, I should say. And that's happening when our velocity is moving in an upward direction, and that goes from t equals 3 to t equals 6. So the velocity is negative, gets closer to 0, reaches 0, and then goes positive, but it's increasing over this whole interval. Acceleration is negative from 0 to 2, and again from 6 to 7, while there's no acceleration or deceleration from 2 to 3. So that means that in this case the velocity is not changing. Okay, we're also asked, when does the particle move at its greatest speed? Well, for speed, we're looking at really the absolute value of the slope, because we're saying that whether the velocity is positive or negative, what we're looking for is the magnitude of the velocity. And so we're going to find that where the slope is the steepest, and that occurs between t is equal to 0 and t is equal to 2, where we have a slope of negative 2, which means that it has a magnitude, or an absolute value, I should say, of 2. And that's where it is changing position most quickly. Its speed is at its greatest. Okay, then we're asked, when does the particle stand still for more than an instant? Well, it does that when its velocity is, so we're looking for any place where its velocity is equal to 0. And all it does is it crosses and just briefly, or really for an instant, has a velocity equal to 0. And that happens at t is equal to 1, t is equal to 5, and again at t is equal to 7. But there really is no place where the particle is standing still for more than an instant. In order to see that, we would have to see a velocity over time of 0. And we do not see that anywhere on this particular graph. Okay, for problem 6, which I don't actually have any diagrams for, the speed of a particle at t equals a is given by the value of the velocity at t is equal to a. That is true. The velocity at the value of the velocity is the value of the first derivative at t is equal to a, and that is the speed of the particle, unless we're talking about a negative velocity, in which case it's not going to give us the speed. We would have to take the absolute value of the velocity in order to get the speed. So be careful about that. B, the acceleration of a particle is the second derivative of the position function. That is true, because acceleration represents the change in velocity. And so really what we're looking at when we look at the derivative of the first derivative is the derivative of velocity, which is looking at the change in velocity, which is what acceleration is. Okay. For 7, we're looking at the instantaneous rate of change in the volume of a cube with respect to side lengths. Well, here we can see as we build this cube that we're tracking here what's happening to the volume, and that's represented by those dots that are climbing up. And what we can see is that it's getting steeper and steeper. The slope is steeper and steeper. The change in volume with each additional increase of, let's say, 1/10 of a unit in the side length, each additional increase is increasing the volume by more and more and more. And the reason for that is because when we think about what the derivative of the volume is, we would actually want to take the second derivative, which would be the derivative of 3x squared, or 6x, because that would give us the change in volume with respect to the change in side length. And so that, since it has a value of 6x, means that as x increases, the change in volume is going to increase as well. And so that's why we're getting this, the slope of our curve increasing, increasing, increasing. Okay, so again, the instantaneous rate of change of the volume of a cube with respect to side length is equal to 6s, the second derivative. All right, for problem number 8, the bacterium problem, we were given that the size of the population at time t is given by 10 to the 6th plus 10 to the 4th t minus 10 cubed t squared. So in other words, we have a quadratic function, and what we can see is that over time it's going to crest and then it's going to start to come down, which means that the bactericide is going to start to take effect and have the net effect of reducing the population. If we take a look at the derivative function, because our original function is quadratic, our derivative function, first derivative, will be linear, and in this case it'll have a negative slope, which means that the rate of change of the bacterium is constantly going down, and so we have a completely concave down situation. So the slope was initially positive, as you can see at the start of our function here, but immediately started heading down towards 0, and then will keep going down in a more and more negative direction. If we look at the growth rates at t equals 0, t equals 5, and t equals 10, we can see that we plug them into our derivative function of negative 200x plus 10,000, and that's going to give us at t equals 0 a growth rate of 10,000 bacterium per hour. At b equals 5, or at t equals 5, a growth rate of 9,000, and at t equals 10, a growth rate of 8,000. So at this point, the bacterium population is still growing because we're still early in the trajectory, right at the beginning here. But after a while, and this is going to happen when our derivative function has a value of 0, which would be when negative 200x is equal, or when 200x is equal to 10,000, which will occur at t is equal to 50. That's when the population is going to start to decline. But again, in the early part of this, it is still increasing, and we can see that it's not until we get to a t of 50 that we're going to get to a 0 and then to a negative rate of change. And again, that corresponds with the vertex of this quadratic here.